Hey there, I'm Alejandro. Welcome back for day 317 of me doing the Daily LeetCode challenge after reach 1 year's worth of green contributions here on GitHub. So today's runs from May 29, 2025. Without further ado, let's get straight into it. Okay. What do we get today? Okay, today we get LeetCode hard from 3373. Maximize the number of target nodes after connecting trees to. Oh, is this just yesterday's problem continuation? Okay, maximize, first of all, it's an optimization problem. Let's read this bad boy. There exist two undirected trees with n and m nodes labeled from 0 to n minus 1, okay. You are given two integer array, okay, m1, in the case that there's a tree, okay, so same setup as yesterday. Node u is target to node v. The number of edges in the path from u to v is even. Note that a node is always target to itself. Return an array of n integers answer, where n survives the maximum possible number of nodes that are target to node I. First tree, if you have to connect one node from the first tree to another node in the second tree. Note that the queries are independent from each other, that is, for every query, wait, is this the same problem as yesterday? What's the difference between this and yesterday? No. Oh, is there no K? Oh, there's no K. So yesterday was with a K. Is that it? Oh, is even. Oh, okay, is even. So that's the difference. Okay. Interesting. Which means what you want to do is just, we just want to do what we did yesterday. We just want to make sure that now we do it with evenness instead of an exact K, right? And we probably want to do even and odd, right? Just because if you add an edge, if you want things that are, if you want things that are even away from this 0 and you add an edge to this 0, then you probably want things that are odd away from this 0, because then that would be even away from this 0, right? Okay. We're gonna do this bad boy. All right, sweet la ba ba ba. Okay, I don't know what I was gonna say. Very first things first is gonna be n comma m is equal to length of edges plus 1. Length of, well, this is gonna be edges 1 plus 1. The only thing, okay, there we go. We're going to do adjacency list of 1 is equal to, we're going to use a list actually, for in range n, for a comma b and edges 1, or say adjacency list of 1 of a dot append b and adjacency list 1 of b dot append I. Same thing with adjacency list 2. We're gonna do this bad boy, but just to be coherent with the problem description over here, they have A, B, U, V. So let's just do that. That's just for the sake of, there you go. This will be U, V, U, V. There we go. Okay, now we've got our two beautiful graphs. Beautiful graphs. Okay, so, yeah. Ooh, to another node in the second tree. I want to look almost at what it said yesterday, right? Okay, yeah, here they're saying connect to nodes 0, 1, 2, 3, and 4, right? I guess you're going to do... Oh, well, obviously, right? Because it's I guess here it's even, so you can make a case for... Interesting, right? Because now it's you could make it find odd stuff away from here, but if I make it like this too, then all of a sudden I can do even stuff. Please P. It depends on how many nodes are in the trees, right? There's at least 2. Oh, there's at least 2. There's at least 2. Okay, so what I'm thinking of is, so yesterday you always wanted to do it from the node itself because you want up to K. Right, but now what's going to be important is for each node, you're going to not only compute its best odd path, but its best even path, right? Because if it's if it has a bigger even, right, or let's say it has a bigger even, it's adding a 0 to an edge from 0 to 0, then it's shucks, I can only use things that are odd away from the 0 because that way it's even away from the 0. But it could go 1 away from the 0, and then be okay, let me grab put an edge from this 2 to this 0, and now all of a sudden I'm allowed to use things that are even away from the 0, right? Because anything that's even away from the 0 is even away from this 0. That's gonna be awesome sauce, super duper awesome. That's what it's gonna be. Okay. We're chilling. Here I'm gonna do def get odd reachability. Here we're going to do self. We're going to take in a node. We're going to take in an adjacency list. We're going to, and it's alt. So we don't take in a k. Returns a list. Here we need node counts, actually. Size node counts. The ith index. How many nodes are reachable from ith node that are an odd distance away? But then it's like there's cycles, right? I'm gonna guess it means like, you know, undirected, but like it's a tree, right? It's like, I'm gonna like, you know, assume common sense here. Okay, we're gonna do that. And then we'll have a get even reachability counts, right? But instead of passing a boolean like, you know, is odd or is even, Uncle Bob says never to do that. Well, actually in this case, you know, we don't have to listen to Uncle Bob. It's LeetCode. There's no code maintainability here. And it would allow me to, you know, do some awesome some spice, yeah? Alright, see it. Get. Right, here we could just do something like def self, comma, node count, comma, adjacency list, comma, true. Return self dots get reachability counts. Node counts, adjacency list, true, get even. Will just be the same thing, but with a beautiful little bit of a false. Alright. Okay. Here we'll say for node in range node counts. Res is equal to this. Here we'll say Q is equal to collections.deck, and here we'll have so this will be the node and path length, right? So initially we're at the very first node. So here we'll say for I, so that we don't have conflicting variables, I and initial path length of 0. And here we'll have a visited set, and initially we will have just node I inside of it. Okay. Now we'll say while Q, yeah? Here we'll say node comma path length is equal to q dot pop left, right? Now we'll say if is odd and parity equals path length modulo 2. Parity equals 1. then res.append. Well, let's relax here. But otherwise it'll be an elif not is odd, and parity equals 0. Right? So let me think. If we have this, if it's odd, here we'll just say reachability counts. Reachability counts plus root 1. Reachability counts plus root 1. Then we'll say for nay in adjacency list of nodes, and visited, then continue, otherwise visited.add that neighbor, and q.append that neighbor with a path length plus 1. Beautiful. And here this is the answer for that node, so here we'll do res.append reachability count, right? And then at the very end we return res. Okay, sweet. So for example, here, let's just do print fstring get even reachability counts of n adjacency list of 1 equals. Let's just confirm. Oh bloody, I didn't put a self, yeah? Okay. Okay. Oh yeah, well, okay. Null was to be expected. Okay, so if reachability counts, let's look at example 1. Okay, so 0 is 1. This is odd, odd, even, even. 3 is indeed what I expect to see. For 1, I see, okay, even here, odd. So, okay, even here, odd, even, odd, odd. So that's the 2. And so, yeah. This is just here and itself. All right, Gucci. Absolutely Gucci. All right, all right, all right. This is just bloody brilliant. Okay. Here, let me just do get old reachability counts. Sorry for my obnoxious, British accent impersonation. I love British accents, and they're fun to impersonate. I do it in pure love, of course. Okay, on reachability counts, so 0. Yeah, this is odd, and this is odd. Yes, yes. 1. This is odd. This is odd. This is. Mwah, mwah. This is perfect. Perfect. Okay. So now, what we shall do, is. Okay. The idea is that since there's at least 2 nodes in the first tree, namely that n greater or equal to 2, here we'll say assert n greater than or equal to 2, we can, since we must apply the operation for every node I, 0 less than or equal to I less than n in the first tree, let I be arbitrary. The idea, we can choose to either 1, connect an edge from node 0, from node I, to another node I prime in the second tree, leaving us with all nodes that are an odd parity away, not reachability away, from node I prime in the second tree to connect an edge from node that is a distance of 1 from node I to node I prime in the second tree, leaving us with all nodes that are an even reachability away from node I prime in the second tree. What this allows us to do is to greedily select the, let me think here, highest varied of any node in the second tree, as we can leverage this result a similar way to have we leveraged the maximum k-1 reachable node in part 1 of this code. Problem. Sweet. Okay. 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 So here we'll say max reachability is equal to max of self dot get m comma adjacency list 2 max of self dot get even reachability counts of m list 2. Okay. Now sweet. I'll do that. Now for each node I first tree, can simply connect an edge from node I, or that is 1 away from node I to obtain the maximum reachability count. Second tree, namely variable max reachability computed above. Okay. Since we are specifically interested in even distances, we will add each node's even reachability count from the first tree and the maximum reachability or even any node in the second tree. This is in similar spirit to part 1 of this code problem. Okay, so here we'll return. So here we'll say is equal to return node counts is equal to n comma adjacency list 1 even reachability counts equals return shareability count plus max reachability and there you go. Something like this. Does this work? No. Whoopsie daisy. Okay. Well, that didn't work at all as I expected. Max reachability equals why is it 1? Yeah, that makes absolutely no sense. Well, that would be bloody why, yeah? There. Okay. And edges 2. Those are the mistakes that are easily made in this world. Yeah, there we go. Okay, accepted. Let's run one more time. Oh, this is gonna be beautiful. This is gonna be beautiful, ladies and gentlemen. Tick tock on the clock. Ba-da-da-da-da-da-da. Is this too slow? TLE, really? How big are the trees this time? They're 10 to the 5. Well, that complicates things. So yeah, this is a correct solution that is too slow. I failed to look at the constraints. I just assumed that it would be like yesterday. Okay, my bad. Ugh. Damn, I was gonna be so happy about that. 60% acceptance rate is not that bad. Yeah, how do we solve this in linear time then? We need to get even reachability or odd reachability. But it's like one part of the tree. How do we dag this tree up? Is this DP solvable? It's like maybe you parse the tree once. No, I'll pair shortest path. Did I actually have single shortest path? Okay. Well, this is a tricky one, yeah? Rip. And there are hints if you need them. Rip. Okay. Okay. Since these are trees, it would be nice to get them as trees. We've solved the Nico problem that is this way, kinda, yeah. Just annoying that it's undirected. Okay. Yeah. Yeah, this obviously works. But it's too slow. So I need to figure out how can I get every node's reachability, pairings, right, or reachability counts with one person tree. Like it'd be nice to know, like, you know, what is it tree node's depth, right? Wow. Yeah. Right, what is their depth? Because that way you can check their massive values. Like, it would be essentially nice to be able to convert these into trees. Just how do I grab something like this and convert it into a tree? That is the question. I've done that type of work before. What did I used to do? Like I get things in degrees. This is in a degree of 0. I have 2. In a degree of 1. Right, I can probably here we'll say first attempt. This is my first attempt solving this problem. So correctly, but inefficiently. We'll keep code. So yeah. Now let's try to solve it better. So still grab these things. It follows spirit similar in nature to my solution to part 1 of this LeetCode. Sweet. Okay, so yeah, let's build those adjacency list tables again. Alright, and here we'll say 1 is equal to 0 times n. Of u plus or equal to 1 in degree 2 of v plus or equal to 1 in degree 1 of a plus or equal to 1 in degree 1 of b plus or equal to 1 in range n in degree of 1. Is dot map like a function? I'm gonna open up my Python here. Python 3 r equals 1, 2, 3. R dot map. It's just not a thing. In degree 1 of is equal to in degree over 2 for in degree and in degree 1. In degree 2 is equal to in degree over 2 for in degree 2. Print f string v1 equals print f string in degree 2 equals. So yeah, so it says like, you know, this could be the root of my tree, or that this could be the root of my tree, and this could be the root of my tree. Oh, that's the only thing, right? Basically, I just gotta pick one root and just stick to it, right? Right, I just gotta pick one that has a quote-unquote in degree of 0, right? Okay. Make the root node of each tree the one with smallest in degree. Right, there we go. Root 1 equals none, comma, infinity for in range n node less than degree 1 is equal to nodes, is equal to degree of node. Okay. Sweet. So now I have the root, right? Yeah. Now, for each node, we shall compute its depth. This will be relevant for dictating whether two nodes are even or odd reachability apart. Depth 1 is equal to Q is equal to collections dot deck. Okay. Okay, depth 1 is equal to none times n. Q is equal to collections dot deck of root 1. Okay. Depth. For neighbor and adjacency list of nodes, Yeah, here we really just need like mini functions. Def best with smallest in degree. We'll take in a in degree. Root comma degree equals none comma float of infinity for node in node counts degree of node of node. Assert root is not none and return root. Alright, so this will be that. Jeez, I'm so laggy. N and in degree 1. This will be with M and in degree 2. Right? Sweet. There we go. So now here we'll say get node depths. Root adjacency list. Right, we could also build a tree, whatever, but yeah. Res is equal to none times n. Assert none not in res. Return res. We'll say q is equal to collections dot deck. Yeah, so here we'll grab the we'll be doing exactly this. Right. Root or q. Assert depth. Res of node is none. Jeez, I'm so laggy. Adjacency list of nodes. If name visited, continue. Otherwise, visited dot add neighbor. And here we'll say q dot append neighbor with depth plus 1. Right. Return depth. Res. So here we'll say depth 1. Assert none not in res. 1 is equal to root 1 adjacency list 1. Holy crap, I am laggy. Depth 2 is equal to this with root 2 adjacency list 2. So basically the nodes that are at even depths, right? Now the idea is that nodes at an even depth are from other nodes at even depth an odd distance away. Depths. This is similar. Okay, things seem to be going back online. I don't know why I'm lagging so hard. I don't have many applications open. Okay. So now that we have this, I can, if you have something at even, print f string depth 1 equals f string depth 2 equals. Okay, print. I don't know what to close. Okay, I can close my terminal application. Like, this is all that I have going. I can terminate that. Then I just have Brave. Okay, I guess my computer is just not handling it today. Root 1 and f string root 1 equals root 2 equals whoops. Where did I make the mistake? In range, node counts. Oh my gosh. Dude, like, I need this computer, like, come on. Is none. Why would this? What? Where is equal to none times n, collections at DAC root 0. How is this possible? Seven? What the heck is node of 7 doing up in here? Did I pass in the wrong? Counts. Holy crap, node counts.
Pero igual la grasa esa se le pega. Se calcina eso.
Okay. Root 1 is equal to, so here it says 1 is the root, sure. Here it says 3 is the root, sure, right? We just make it a root of the tree, and like technically, like, you know, this is the root, and then this is the child, and then this is the children that has these children, and so on. The point is it's the one with smallest degree. You might as well make it the root, right? The point is you can't, I guess you could make any node the root. You don't even have to pick the one with the smallest degree. Anything can be a root. This just means that this guy has 3 children. I'm actually kind of dumb. Dude, this is so laggy, it's not even funny. But I don't know what to do with my computer. It's just lagging like crazy. It's not handling. Let me empty my trash. Empty my trash. There we go. Maybe it's a little faster now. Let me increase the brightness. Because like I have nothing running in the background. Okay. After turning this up, I now realize I can just make any node of it. But okay. Well, that's a rip. So now we have node depths. So I say so let's just make 0 the root every time for easier testing. If it lets me type it out. Because my computer is slow. Okay. Root 1 equals root 2 equals 0. Okay. Depth. So this is a depth of 0, depth of 1, depth of 1, depth of 2, depth of 2, right. 0 is a depth of 0. Then it's like 1 has a depth of 1, 2 is a depth of 1, 3 is a depth of 1, 4 has a depth of 2, 5 does have a depth of 3, 6 does have a depth of 3, and 7 does have a depth of 2. So we're getting depths correctly, right? So let's just say sum holy crap, 0 and 2. Sorry, it's just I'm getting frustrated at just like this computer not being able to handle anything right now. Some odd 1, range 1 and 2. Some even 2. Depth 2 of I, depth 2 of I, depth 2 of print f string. Some even 1. Prints. Come on. Come on, LeetCode, you can do it. Okay, this will be come on, LeetCode, you can do this. Some even. So here we'll put a print. Some even 1. Okay, so it's like this is Even, so 3, yeah. Some odd, this is odd, it should be 2. What the heck? Oh, no, it just measures the node's depth. Yeah, some even 1. I'm doing this wrong. Holy crap, this is just such a slow process. Okay. Holy crap. So, this is even, odd, even. So what's going on here? It's modulo 2, or 1. Well, that's why. It's because I'm doing this. And there should be M. There should be M. Oh boy. Sweet. Even, odd. Now here it's even, 3 evens. And odds is 1 odd, 2 odds, 3 odds, 4 odds, 5 odds. Good. Holy crap. Okay. Oh. So the maximum reachability will just be this, right? So then, using same trick as in attempt below, we can take max of sum even 2 and sum 2, snap it to reachability of every node. Tree 1. This is because in either access add an edge from node I and node 1 distance away. Greedily pick more even reachability. It's in the, if it doesn't freeze up, second tree. Okay. Okay, so now, yeah, let's do max reachability is equal to max of sum even 2 sum onto. We'll be able to add either thing we want. Now, for each node in the first tree, we will want all the ones that are even reachable from that node. Moreover, all the nodes share same parity in depth level. I don't know what's going on with my computer. The same parity in depth level. Similar for similarly. All right. Return for node in range n is equal to this. We'll get if is even depth. Come on. Equals to depth 1, okay, of node, my computer, modulo 2 equal 0. Of course, it just decides to add a period, yeah? Gosh, I'm gonna kill this laptop. Is even depth, if is even depth, sum even 1, if is even depth, now sum even sum odd 1. Res.append reachability plus max reachability. Holy crap, this is just so slow. Return res. Debugging this is going to be a nightmare. Okay, I'm going to give the computer 3 seconds here. Just like, you know, get some speed going. Alright, run. Okay, that is accepted. Let's submit. Boom shakalaka. Completion streak 317 days. Consistency is key. See ya tomorrow. Oh boy, does that feel good. Hell yes. Absolute hell yes. Okay. Holy crap. My computer is so slow though. Oh my goodness. It's not even funny. Oh my. Comments. Dude. Okay, I'm gonna, how many prints are there? There's 3. How many 10. Okay, so I need to find the yeah, there they are. Okay, so now when I run this, okay, no prints. Submit. Dude, my computer is just not handling it today. Okay, 567 ms, speeds 30.68%. I'll take it. Just my computer is just dying, so I'm just gonna leave it as is. Okay, so nevertheless, as always in my videos, I do a quick recap if I just solve the problem. So for this one, it really built off my solution to yesterday's problem. So in order to solve this one, I had to do yesterday's problem, which essentially, if you recall, a node U is target to node V if the number of edges on the path from U to V is well, in this problem is if it's even, right? So essentially the shortest path from U to V, note this is an undirected tree, right? Meaning that, you know, there's going to be m minus 1 edges for the first tree with n nodes, and m minus 1 edges for the second tree with m nodes and so on, and edges 1, edges 2 gives us like, all the edges in the first tree, all the edges in the second tree, yada yada yada. Same setup as yesterday. In yesterday's problem, we were also given an integer k, and it was like, find all the nodes reachable from u to v. Find for every single node in the first tree, return to me all the nodes that are reachable by distance of like, at most k, right? And you're also allowed to add an edge from the first tree to the second tree. And so what you would do is like, okay, if you're at node 0 in the first tree, right? Oh my goodness, okay. For example, with k is equal to 2, then you're like, okay, 0 itself, well, it's 0 away, so it's less than or equal to 2, so that's good. This is 1 away, so that's good. This is 1 away, that's good. 2 away, that's good. 2 away, that's good. If there was something even deeper, though, it wouldn't be good, right? And then you can connect an edge from any node here to any node here. So what you did is you greedily went from the node that you're currently at, right? Because you want things that are less than or equal to k away from 0. So like if you did it from 2, then like, anything else must be like, less than or equal to k minus 1 away from this 2. So you greedily chose the 0 to plug an edge to the second tree, and you essentially greedily picked the one that had like, the most nodes that were at most k minus 1 distance away, right? Because here's like, you use one edge to get to here, and then you can only get to nodes that are like, k minus 1 edges apart. So you just spend time finding like, the node that has the most amount of neighbors that are less than or equal to k minus 1 edges away, including itself, and for each node essentially plugging it with that, right? Using itself. Now here we're interested in essentially even paths. So that means like, a node U is targeted to a node V, not if the number of edges is less than or equal to k for some input k, but if the number of edges is even, right? And this is a tree, so there's no like, cycles or whatever, even though it's an undirected tree, yada, 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 right? Here also, since I make the, I'm gonna do two things that might make my problem faster. Either this, nope, or just not spending any time. Actually, since I don't use the function, I'm not spending any time on that anyways. So my apologies. Sorry, this is just me doing something on the side here. Yeah, okay, sorry. Okay, description. Okay. So what I did, and you'll have to forgive me here because of a very slow computer, is very first things I computed n and m. I know that the number of edges is n minus 1, so length of edges plus 1 will give me n, and same thing for m with edges 2. I built an adjacency list for the very first tree and the very second tree, right? For every single like, uv and edges 2, I add an edge from u to v, add an edge from v to u because it's undirected, and here I have like my in degrees thing that I actually do not need anymore, because this was for getting the root. So what I was doing is I was essentially saying, okay, I can't do it the way that I did it yesterday with even and odds, which was the very first thing I tried, and I have all these beautiful comments here for, because the constraints are as follows. N and m are less than or equal to 10 to the 5. In yesterday's problem, it was less than or equal to 1,000, meaning that you could have n squared or m squared solutions, yada, 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 right? Or n squared plus m squared solutions. Here you cannot, you must do it in linear time. So I had a correct solution that was too slow, and I had to think about how to do things better, right? In this one, what I did was very, very simple. I essentially, like, in the first tree, I essentially went through every single node, and for each node, I was like, okay, how many nodes are like, even away, even apart from it, or odd apart from it, right? And so I had two functions, one for like, getting odd reachability counts of every single node in the tree, even reachability counts in every node in the tree, but like, I was doing an O of, a breadth first search for every single node, so like, O of m time for all O of m many nodes, meaning O of m squared time, which is just not allowed, right? So I cannot solve it in a spirit similar to yesterday, just because I must have a linear solution, not a quadratic solution. Okay, so that's not a worry in the world, because I came up with a different approach. Okay. Yada, yada, yada. So what I did, essentially, is I realized, okay, since we care about even and odd, and this is a tree, how about we leverage the fact that it's a tree to essentially assign a depth at every node. And that way, we know that if a node is at depth 4 and depth 8, then they must be even length apart, right? Because even if like, they're on both sides of the tree, it's like, from depth 4, let's say you want to get to depth 3, you take one edge, and you want to get to depth 4 on the other side, you take one edge, right? Well, you took two edges, you took an even amount of edges to get back to depth 4 another level, right? And so on. And to get to depth 6, it's like you must take one edge to a node in depth 5, and then another edge to a node in depth 6, right? So it's like it becomes even, right? So every single depth change requires one edge, right? But that way, it's like, two nodes, if their depths are even, then they're even apart. If their depth parities are odd and even, then they're odd apart, right? That's kind of the idea. So what I wanted to do is essentially treat the fact that these are undirected trees, and for each node get its depth, right? So that's exactly what I did. So first, what I need is the root nodes of each tree. Now, since this is an undirected tree, what I was doing at the beginning is I was essentially, getting the node with the smallest integer to be the root node. I realized I can actually do any node, right? So like what I was doing is like, for example, here, 3 was making it my root node, right? Because it's like it has the smallest amount of edges, and that way 3 is the root node. It has one child, which is 0. 0 is 2 children, which is 2 and 1. Then the 2 child has a 7. So like, you can kind of visualize it, right? It's like this 3, you're like pulling it upwards, and you have everything underneath it, right? But even something like 4, I can make it my root, right? It just means that this guy is going to have 3 children, which is 5, 6, and 1, right? And like these guys have no subchildren, but this guy has more subchildren, right? It's like I'm grabbing the 4 and getting at the top. The point is I can make any node my root node. So I essentially realized that, and then it's like, okay, this function is now useless. I commented out this code, and it just said, okay, root 1, root 2, I'm just going to set it to 0 by default no matter what. Then what I did is I'm like, okay, now that I have the root node of each tree, I want to figure out the depth of each node. And we've done this a million times in the NICO 115 and the LeetCode challenges. You just do a breadth first search from the root all the way down and get those depths, right? So here I do, and again, since the graph is still undirected, you do have to use a visit set, yada yada yada. Here I don't actually care about building the tree. I just care about getting the depths of each node. Right, so here res, my depth is going to be equal to none times node count at the very beginning, just because I'm being cheeky here. Just like, I need a placeholder value. I could just make it like, dictionary. It doesn't really matter. But here I'm going to say, okay, q is equal to collections.dec with root and 0, right? So this takes in a root, a node count, and an adjacency list. Why? Because I want to do it. Okay, sorry. I want to do it. This is a function that I'm making because I want to get the node depths for the first tree and the second tree. The first tree and the second tree will obviously have a different root node. They obviously have a different number of nodes, and they have different adjacency lists, which I pre-computed here at the beginning, right? So that's why I take these 3 parameters just to define which tree to use, right? But otherwise, res is equal to none times node count. Q is equal, okay, we're going to start BFS starting from the root node with a depth of 0, right? We're going to add that to our visited set and just keep going until the Q is empty, right? So while Q, okay, let's pop node and depth from the left of the Q, assert that obviously I haven't set the depth, and just say, okay, res of node is equal to depth, right? So these are my depths that I'm going to return. So it's like, okay, this node has this depth, right? We just pop this node with this depth, so that node in res, I'm going to set it to this depth, right? Then I'm going to go through every single neighbor in my adjacency list that is not visited. So if it's visited, then continue. Remember, this is important because we have an undirected graph here. So even though it's a tree, like, you got to make sure like you structure it as a tree. We're going to say, okay, otherwise, if it's not visited, then we know that essentially it's like, if we were at node 0 and we're visiting node 1, it's like if 0 is our root, then it's like, okay, 1 is like one of my children, right? So if this has a depth of depth, then this guy is going to have a depth plus 1 total depth, right? So I will add it to my queue as my neighbor with a depth plus 1, right? And then at the end, what I'll do is, okay, assert none in res. I assigned every single node a depth because initially I set them to none, and then just return my result of depths, right? So depth 1 will be, get node depth with root 1 and an adjacency list 1 to get the depths of the first tree, and similar for depth 2 for getting the depths of the second tree, right? So that way index I of depth 1 will be the ith node's depth, right? That's kind of the point. So then what I do is I'm like, okay. So let's think about this. For every single node here, right, the idea was this. So what I did in the below was kind of smart, which I said like, okay, we want for every node to essentially get like, the maximum target nodes, right, the most amount that you can reach, right, and you can only reach things that are even away. And notice here, there's at least 2 nodes in the tree. This is very important. So it only matters that there's at least 2 nodes in the first tree, but ignore this for now. Without loss of generality, let's just focus on node 0 here, but we're going to apply the same thing for every single node. Let's think about this. First of all, we have to get all the nodes that are even away from it, right? So what we can do is we can essentially get the depth of this node, right? In this case, let's say it's depth 0 because this is our root, right? We set 0 to our root in these problems. Just happens to be my root node. So everything that's going to be even away from it is going to be everything that is at an even depth level. So that's why I compute here the sum, the number of nodes that have an even depth, and call this sum even 1, and the number of nodes that have an odd depth, call this sum odd 1, right? In this case, 0 is my root node, so depth of 0 is an even depth. I'm saying, okay, it's reachable at an even distance to the total number of nodes that have an even depth, right? Remember, nodes at an even depth will be even away from nodes at an even depth. Nodes at an odd depth will be even away from nodes at an odd depth, right? The point is, if you have a node at depth 4 and you're trying to get to depth 6, right? Maybe it's like you're on one side of the tree, you have to get to depth 3 and then depth 4 again, but that took 2 edges, so you're still even away. To get to depth 5 takes 1, so now you're odd, but then to get to depth 6 it takes another 1, so now you're even. So the point is, as long as the same depth levels are the same parity of even or odd, then you guys are even apart, right? So odd depth nodes are even away from other odd depth nodes. Even depth nodes are even away from other even depth nodes, right? In this case, 0 is at depth 0. It's a root node, so it's even away from even depth nodes. The number of even depth nodes, I put that in sum even 1. The number of odd depth nodes, I put this in sum odd 1, right? So I pre-compute this in O of n time, right? So it's for each depth, for I in range n, get depth 1 of I and modulate it by 2. If it's 0, that means it's even parity, right? So it's sum of all the ones with. Okay, my recording is going. Sorry, I'm super sorry about I don't know how this is gonna look like in the recording. It just keeps cutting and so on because I don't know. I don't have any background tasks, but it's just my computer's really bad today. Okay. Nevertheless, sum even 1. So yeah, sum even 1 is the number of nodes at even depth levels in the first tree. This is the number of nodes at odd depth levels in the first tree. And then I do the same thing for the second tree and the for even and odd, right? So given that, well, okay, so this is at an even depth. So how many nodes are at an even depth? Well, this node is at an even depth, this node is at an even depth, and this node is at an even depth, right? This is at depth 1, depth 1, depth 2, depth 2. So even, even, even. So there's 3 nodes at even depths. So this is even away from 3 nodes, which is good, right? It's 0, 3, and 4. Now we want to maximize the reachability of this node, which is nodes that are even apart. So let's focus on 0, for example, right? First of all, right, let's say I connect an edge from 0 to 0, right? 0 is 1 away from this 0. So already these guys are odd apart. I cannot include this 0, which means that I can only include things that are odd apart from this 0 in the second tree, right? Because, for example, this 2 is 1 away from this, so it's odd apart. Since it's odd apart from this 0 and this is odd apart from this 0, it is 1, 2, even number of edges apart between this 0 and this 2, right? And this is the one that we want to maximize the reachability or target value for, quote unquote, right? So if I add an edge from this 0 to this 0, then all that matters is the number of nodes that are odd reachable from this guy, right? And that doesn't stop there. In yesterday's problem, it was advantageous to greedily put an edge from the current node we're going to the other tree, right? Because we're talking about you must use less than or equal to k edges to get to other nodes. So it's you might as well put an edge from the node that you're trying to maximize from to the second tree to the best one, right? Here we don't have to do that, right? Because let's say 0 had 1. Okay, obviously here it doesn't have just one odd neighbor, blah blah blah. Right, but for let's say it had 0 odd neighbors, right? But let's say it had 10 even neighbors, right? And it's shucks, right? I add an edge from here. It's I can only include this guy's odd neighbors, right? So then, shoot, it's just plus 0, right? How could I get its even neighbors? Well, I could just come here. Instead of adding an edge from node 0, I could go to a node that's 1 away from node 0. For example, either this 2 or this 1, right? Let's say this 2, for example. And then add an edge from this 2 to this 0. And now all of a sudden this 0 is even away from this node. And now what will count is nodes that are even away from this node as well. So I can either choose, I can basically choose any node and either get all the nodes that are even away from it or odd away from it, right? If I want all the ones that are, for example, if I want node 1 and I want all the ones that are odd away from it, I can just put an edge from 0 to 1. If I want all the ones that are even away from it, I can just go 1 away from the 0, so for example this 2, and add an edge from here to here. And now you might be asking like, okay, well how do you know there's always at least, one node that's 1 away from you here? Well, because the constraints specify that n is at least 2. So there's always at least 2 nodes in the first tree, right? So I can always pick a node that's at least, 1 away, and it's, it's a connected tree, it's one connected component. I can always do this. There's always at least one neighbor. So I can just always do this, right? And that's pretty much the awesome sauce trick. So what I do is I compute out of every single node in the second tree, what is the maximum reachability, whether it is odd or even, right? For each node, get its even node reachability and its odd node reachability, and take the max out of every node, because then I'm going to plug and play that node for every single node in the first tree, in similar spirit to yesterday's problem, right? So what I do here is I take the max between sum even 2 and sum odd 2, right? Because for every single node at an even depth in the second tree, the number of even reachable nodes away from it will be sum even 2. The number of odd reachable nodes away from it will be sum odd 2. And every single node is either, at an even depth or an odd depth, so these are really the only two options. So that's why I take the max of these two values as my quote-unquote max reachability, similar to yesterday's problem. And then from then on, it's just cake, right? Here's just like, okay, for every node, we're going to get its the number of nodes that are even away from it, so we get its depth level. If the depth level is even, then let's use sum even 1, because that's the number of nodes that are at even depths. Otherwise, if the node's depth level is odd, then let's get all the nodes that are an odd depth level, right? So here's like, okay, is even depth, so for each node in the range n, it's like, okay, is it an even depth? Well, let's check that node's depth. If modulo 2 is equal to 0, then it is even. So its reachability is, well, if it's an even depth, then get the sum of all the nodes that are even depth levels, because those are the ones that are even reachable apart. Otherwise, if it's not even depth and it's an odd depth, then it's even reachable to other nodes that have odd depths, right? So sum odd 1, right? And then what are we going to append to our result? Well, that reachability, right? Reachability represents, like, for example, for node 0, the value will be 3, i.e. there's 3 nodes that are even reachable from 0 because it's an even depth, and there's 3 nodes at even depths, plus out of every single node in the tree 2, right, get the max reachability. If sum even 2 is the larger one, then that means we want even parity nodes. So we'll be like, okay, from 0, don't pick 0, pick a node that's 1 away from 0, and then add an edge from that to the best one here and use sum even 2, right? Or otherwise do the opposite thing, add an edge from 0 and then use sum odd 2, right? So we'll add max reachability for every single node as a fixed value, similar to how we did yesterday to the original reachability. And we'll do that for every single node and then return result, and there we go. Bada bing, bada boom, we have a reasonably working solution to this problem. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any shape or form, I'd highly appreciate it if you left a like or a comment. But otherwise, I'll catch you next one. So until then, ciao, ciao, my friend. Bye-bye.